Okay, so let's understand the famous problem of the trade-off between bias and variance. So this is pretty advanced because this is more about the problems that you face when you're actually implementing machine learning algorithms. And if this is the first time you're ever seeing a video on machine learning, then this is not for you. The assumption here is that you already are familiar with at least regression models. Okay. So anyway, we'll cover everything. We'll cover regression models in a rough way just to brush up the concepts in this, but this is not for the beginners. All right. So let's look at what we have here. We have bias variance trade-off, and let's understand first the definitions, the jargons. And right now, when I define this, I read this out, you'll not be able to follow it if you haven't understood it yet. But I'll assure you, once we finish this video, um, we'll be able to understand and appreciate the meaning of these definitions. Okay, so bias is how far removed the mean of your predicted value is from the real answer. And variance is how scattered your predicted values are from the real answer. Both your bias and variance are calculated on how your model performed over the testing data. Okay, how well it modeled. So let's say what we have on the side of the circles, pink, green, and white. Let us say this pink field is a field where if your answers are somewhere over this region, if your prediction is good, so it'll fall off here. And if your prediction is really bad, then this is where it'll fall. And if your prediction is average, then this is where you'll end up, this band. Okay. So this is more like the quintessential problem of, you can relate it to accuracy. You know, this problem, these definitions of what is accuracy, and what is precision. So uh, in a way, you can say accuracy is measuring your bias, and precision is more about measuring your variance. Okay, we'll see that. We'll just check this. I made a mistake. I made a mistake. I don't want to make a mistake. Yeah, yeah, fine. All right. So I have this small scattered point set data sets here, right? So this, let me take this. Let's say this is your, these are the points that were predicted by a model, these pink points that you see. Let's say these are the points that were predicted. So now if this prediction point happened to fall here, means nearer to your expectation, this condition is when what we call a very ideal, nice condition. And ideally, we would call this a situation of low bias and low variance. Very nice model if we achieve this, right? Ideally, this is achieved when you have all realistic conditions. Especially this kind of models actually appear when somebody is actually giving you a tuition on machine learning and they have selected nice, beautiful data that falls right everywhere. And that's what you do when you're teaching, so that you're conveying the concept. But in real life, this is not going to happen. So that's why this I told you that this lecture is not for somebody who begins, because it's more about when you start applying machine learning models, these are the kinds of issues that come up. Okay, so let's now move this model of ours. Where were we? We were here. Okay. What if this is here? What is this condition? This is the condition. This is what we call a state of high bias and low variance. Okay. High bias is, let's go back again to the definition of bias. Bias was what? Bias is how far removed the mean of your predicted value. Now, what's the mean of your predicted value? Where is it? The mean of your predicted value is somewhere over here, right? So what happens to this? How far is it? Check this out. It's very far. Okay. So if this mean of the predicted value is far away from what you wanted to achieve, then you've got a high bias situation. What if instead of this, instead of, let's say this was our answer, okay? So we bring it here and we've achieved this result, what is in front of you. In such a situation, what we call this situation is the situation of what? Situation of low bias or medium bias, because see the mean of it is what? The mean of it is actually here, isn't it? Low bias, but the variance is not, let's say, high, but sort of high. Okay. So what would be a really, we'll draw that. This is low bias and let's say medium variance. Now, if I attempt to draw something which would be more like a low bias and high variance, how would it look? It would look something like, let's attempt to draw it. It would look something like this. Right. And then we would attempt to bring this particular segment. I'll have to erase these things, of course. And I'm going to have to bring this data here. I'm going to make it red. Okay, let's talk about this red dots that we have. So for all these red dots that we have here, if red dots, not the pink ones, the red ones. Okay, so if the red ones are in contention, if that is what we're discussing about, then that is the case where the red dots being the data, this is a case of high variance. And when you calculate the Euclidean mean of it again, you still end up with low bias. Because bias is when you end up with values which are moving away, like this. Okay, this is high bias and low variance. As it moves to the center, it's low bias and low variance. So I hope you get the point. That's what it is. It's more like accuracy and precision. So let's see how it happens. Let's see how it happens in real life. What happens and why such situations, we find ourselves in such situations. But before I get there, it's good time, because now that we have understood the model, it's good time to just go through these bullet points. So variance is how scattered your predicted values are from real answer, and bias is how far away the mean of your predicted value is from real answer. And our contention is to, our work is to be able to balance both of these. So your actual error in your model, your actual error in prediction is bias squared plus variance. That's the equation. So it's the error that you want to minimize and not bias or variance specifically. Okay, so that's very important that you understand this. When you say let's decrease the error or increase the accuracy, so increasing the accuracy, sometimes you want to increase the number of data that you have or clear the data or pre-process the data in a better way, but also sometimes decreasing the error is also attributed with the idea of increasing the accuracy, and decreasing the error is about bias and variance. And this is how it is: you there is a twofold decrease in bias and a one-fold decrease in variance. Okay, that's the equation. That's what this equation says. Anyway, a complex model will have high variance and low bias. Yeah, I agree with that. You will be able to agree with this once you see the data. And a too simple model will have low variance and high bias. Yes, again, true. So we'll understand what this means, or these, after I give you the example that we are going to follow now, you should be able to revisit these statements and appreciate the meaning of it. Okay, sometimes some certain points are really difficult to put across, and too much data has to be seen, but this is the kind of intuition that you arrive at. And when you start appreciating these kind of statements, you can start telling yourself that, okay, that you have matured, yourself, evolved into being a certain kind of a data scientist that you want to be. And so the idea is both may have the same error, complex model and simple model, but the optimal complexity is in the middle. Okay, so you want to always be at this. So we'll understand what it means, what this trade-off is. It's interesting. We have a simple example here. So, okay. So let's have this simple example where let this be the given data. Okay, let's not look at that. Let this be the given data. Some random data we have, and I'm going to reset this data to the center. We are not drawing. We're not concerned about Excel sheets and rows and columns. We're a very state where we can understand now that this is our data. This is how it gets plotted. And this is graphical explanation of bias and variance anyways. So let's understand this. Somebody has given you this data, age and income. Okay, and this relationship what I have drawn, it may not be true. This is an experimental data. It's not always true that with age income increases, right? Maybe 70 years ago it used to happen, I don't know, but right now you'll see a lot of variations. Anyway, some ideal data we have. All these greenish white points are the data represented on a 2D graph with age on x-axis and income. So what do you do first when you have data? You separate them into training and testing. So I've got a colored pictorial separation done. Where is it? It's here. Let's come down. Yeah. Okay. So let this be the given data after separation of training and testing data, right? So what is the blue? What are the blue dots here? Blue dots are all our training data. What are the pink dots? The testing data. Okay, I see that there is no property, so I'm going to draw that. Okay, now it becomes a testing data. All right. So from this, what we have to do, we have to remove the testing data from it and train the model on the training data, right? So I removed it. I've removed the pink values out, and we have separate them. So removed means I've separated them. See, we have our training data now, and we have testing data. Yeah, both training and testing data. Good. All right. So we are going to apply simple models on this. Let's say we start with linear regression. Okay, we're going to apply linear regression on this. Where's our linear regression? So what do we do here when we apply linear regression? We cut across this. We try to fit in a line, right? A simple, nice y is equal to mx plus c line. And what is your y is equal to mx plus c line do? What does it do? This line is y is equal to mx plus c. Of course, this C, let's say, is here, is the y-intercept, and your M is the slope, right? So the slope looks roughly about 35% to me, 0.35. So yeah, so your this equation will be actually y is equal to, if your C, let's say, if this is 0 comma 0, and we've scaled it to 1, 10, 20, right? So your C is at somewhere at 10. So your model actually is somewhere around 0.35 x plus 10. This is your model, right? This is the fit. And the least squared algorithm went through its process to fit the data. It went across this, right? And finally it found the right kind of C to fit across, to achieve what? To achieve minimum distance between these points, the Euclidean distance, right? This is what it is trying to minimize all the time. That's what your least square method does. Anyway, so after that we have R squared value, which defined as the percentage of points that the model is able to capture. So Y inspection, this is a graphical example that I created. So follow along. And what we have here, we have this point, this point, this point, and these points are all out. So roughly about, I think we can do a better model here. Let me do it. I think I just saw that, right? We can actually do a better model of this. Let me go like this and push this one here and this one a little further below. Now this looks like a better model to me. Yeah, this is capturing more number. So we sort of now have this as the outlier, this particular point. So roughly everything else is about that line. So yeah, so if that is true, then what we have here is about 80%. Okay, we've got an 80% fit on linear regression. And let's say this is not enough. So we want to go all out, and y is equal to mx plus c, because it's a monomial equation. The order of the equation is 1. So that's why we have a straight line. We want a model that can push across all these dimensions, and we want a model that fits the training data perfectly. In that case, what do? We go for polynomial regression. So in that case, when we go for polynomial regression, we achieve what we wanted. This polynomial regression again is, how does it work? Instead of your simple y is equal to mx plus c, you have a polynomial relationship here, which is more like a1 x square plus a2x. Okay, this one is x raised to n, x raised to n minus 1, a3 x raised to n minus 2, dot dot dot, a k x raised to n minus k minus 1 in this case. Okay, and who defines, how do you know from which order this should start? Intuitively, as we've already studied in our previous lectures, the intuition for this order comes from how many times there is a change. It's like, this is one linear regression, y is equal to mx plus c, then there is another change here. So these are the points where the changes happen. So roughly based on this, you'll get a polynomial order of the polynomial equation. So roughly what, 1, 2, 3, 4, 5, 6, roughly about a 6th order equation is due here, right? You had to go all the way to a 6th order equation to fit a model perfectly to your line, perfectly to your training data, and achieve an R square of 98%. Again, what is R square? R square is the percentage of points that a model is able to capture. Points is what? Variance. Percentage of points is the percentage of variance that the model is able to capture. In your training data, what you're looking at now is perfect polynomial equation, which has captured all the variations. Okay, high weight, good, low variation model. But how does it perform on the testing data? Is what is where is the money. Okay, it's not about how well you perform on the training data, it's about how well you perform on the testing data. Training is an ideal world, a sample collected out of the population. You did your best, you applied all the tricks and trade in the book, and from your experience you got some model. But how does it work on the testing data? So let's see. Okay, now this was our testing data. Okay, so so where did I get it from? Let me get that whole thing back. So we don't forget. Let's copy this and keep it with us. Copy back here. Yeah, let's copy this here. Right. And let me zoom out of it. Right. So there's no doubt now. All right. So what do we have here? We have the testing data not performing as well as we wanted, right? So that's what happened here. What is the R square? Roughly about the R squared value here is roughly about, okay, the number of points 1, 2, 3, 4, 5, 6, 6 on 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 6 on 13, that's roughly about 60 or 55%. And what was so good, 98% on your testing data, on your training data, sorry, underperformed on your testing data. Let's go and look at what happened with the linear regression. Now, if this is the line that we're talking about, and this is your model on your training data, the model on your testing data is still consistent, right? This is the same model, right? Let's see. Copy, paste. Let's bring this model here. Yeah. And the other model is gone. Look at this. It has sort of captured roughly around all the variance. Although the bias is high or not so high, there is a certain amount of bias, there is a certain amount of variance. Both are there. But what is the end result of it? How much is it able to? Let's calculate it. Roughly about, these points are low bias, this is high, and this is high too. So you got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 out of 13. That's almost again about 75% or 80%. So this model, linear regression, although we were able to fit the model perfectly in polynomial using all your high funda complex polynomial equations here, it underperformed because this is overfit. You're overfitting this. This is what is looks good but doesn't work out. This is exactly what overfitting is. Sometimes you feel that perfect, you did everything right, but as and when you start testing a model in the real world, you're not able to achieve that, right? But when you had a when you allowed for that trade-off, that balance, right? The balance between bias and variance, you ended up with consistency. Okay, so this is the moral of the story. The whole idea is to be able to consistent in your model, means your model should be able to be consistent in what, in capturing both the bias and the variance of the what, of the training data. If you achieve this balance, then you will have good results on the testing data. Okay, so that's the whole idea. Sometimes it's not possible. I'm not saying every time you will be able to do it. Sometimes you're not going to be able to get that balance out because the data is, because of high number of features. Okay, so and you end up with a classification problem and you're not able to balance it properly. So that's when classifiers like SVM come into picture. And how SVM does classification is at a different level. We're going to learn that also. But this is the whole idea. This is all the crux. This is all the matter that I wanted to discuss in this one. So remember this every time. Next time you have this, you know, sudden feeling that after doing everything right, you're still not able to achieve that model. It's because you're not allowed for that um, balance to happen. And when I talk about SVM here, that same trade-off, I mean, I know I'm digressing from this, but for those people who have studied a little bit of SVM, they will be able to appreciate it. That C factor that you talk about is that trade-off that you're allowing, the misclassification that you're allowing in SVMs. That is sort of correlated, or the idea is, the intuition for it is directly related to this balance that we have been talking about from a long time, right? Balance between bias and variance. So anyway, I hope you found this video interesting, and let me know if you have any doubts. I could clear it later on our one-on-one doubt sessions, but you can also post the doubts on the description or the comments below. All right. Thank you.